So thank you very much, everybody. I'm Andrea Barizani. I'm from Italy, which is why I have a girly name for every country other than Italy. But this is me. This is my first Congress, by the way, even if I live so close to here. I feel very privileged to be here. And so far, I've been very overwhelmed by the quality and the people of this event. So I'm really happy to be here. And thank you for coming to my lecture. So I did this talk with Daniele Bianco, my colleague at Inverspath. So just to give you a brief introduction of what we do, we're a consulting company. We did a lot of exotic talks in the past years. We were one of the first ones to do talks about car hacking. We sniff keystrokes from the power line and with lasers. In 2011, we did a chip and pin talk, and this is an updated version of that with new findings. Last year, we were one of the first ones to do packet in Ethernet and so on. And tomorrow, just a little ad, I will have another talk at 5:30 here about the USB Armory, which is our latest hardware project. So EMV, I'm going to talk about the credit cards with a chip that you have, which is called chip and pin in UK. EMV is the name of the standard. And we addressed this topic a few times in the past. And the reason why I'm doing this talk is because working in the security industry, I really dislike where a technology, which is supposed to be secure, but it's really not, it's used against the users of that technology. Because it should be the other way around, right? I mean, if you use a secure technology, whatever that might mean, it should protect you. It should be something that works for you, not against you. And the problem that we found in the past with EMV, along with the fine folks at Cambridge as well, they also published research about this, is that the way EMV is being marketed and used on a legal standpoint is, in some cases, not all cases, against the users. And we're strongly against that, which is why we're making these talks. So EMV is the name of a standard that regulates, every time you see a credit card with a chip, that's EMV. That's what we're going to talk about. So you have a smart card, which of course, this is undeniable. It improves the security over the existing Magstripe, which you still have, by the way. I mean, every credit card nowadays has the chip, the Magstripe, and the embossing as well. So you still can fall back to very old technology there. So EMV was invented to replace the magnetic stripe. It was invented also to promote offline card verification and transaction approval. So to give you the ability of validate a transaction without taking the cost and the time of going online to the actual backend. And you can have multiple applications on one card. You can have credit and debit if you want. So these were the main reasons for moving to EMV, which are good reasons in a way. One of the other reasons is that with EMV, you promote a liability shift. So the liability shifts away from the merchant to the bank, in theory, but the cardholder, which is you, which are, the user of the card, is assumed to be liable in most cases, unless you can unquestionably prove that you were not at fault into protecting the PIN or whatever credentials have been used for the fraudulent transaction. So this is the core issue here. With EMV, the PIN verification becomes proof of your presence. Now, if the technology cannot ultimately protect the PIN, then, of course, this liability shift should not happen at all. And this is what we're going to address in this talk. This is a very nice example. Canadian Imperial Bank of Commerce. A guy was frauded for $81,276. Our records show that this was a chip and PIN transaction. This means the customer personal card and personal PIN number were used in carrying out this transaction. As a result, the customer is liable for the transaction. So this is the problem. By the way, the thief bought a race car. That's the sum, 81,000, which is what I would do. If I would have to fraud one of your credit cards, that's what I would do. I would buy a race car. I think it's a very good thing to do. But sadly, with chip and PIN, you might be liable, and I don't want to do that. I mean, if I can get my race car and you can get your money back, I think it's a win-win scenario. So if anybody wants to do that, we can talk about it. So EMV is broken. So this is the best presentations that have been done about EMV. One is mine, but I'm not biased by any means. So the guys from Cambridge did an excellent job with the chip and pin is broken research. We did one called chip and pin is definitely broken with our friends at Aperture Labs, Adam Laurie and Zach Franken. And then there was the next one about pre-play attacks. I'm going to address all of the issues that have been presented here, and then one more, which is a combination interaction between two of these talks here, which is something new that has never been presented before. So you're all familiar with ATM skimmers, I guess. If not, you should. Like when you go to an ATM, keep in mind that there can always be a fake PIN pad and a fake credit card reader. So EMV and the chip was designed to prevent this, to find ways where the Magstripe, can go away so that it would not be so easy to intercept everything that is read while you put the card inside. But our point was that we can do EMV skimmers. So this is a very tiny, very thin EMV skimmer that we did for research with our friends at Aperture Labs that can be covertly inserted into a point-of-sale device. So this device has a reader, a smart card reader, and it's two faces. So it acts as a shim, as a man-in-the-middle device. And it can be placed inside a point-of-sale device. So when you insert your card, the card is being intercepted by this device. And once it's plugged inside, you cannot even take it out easily. It's so covered that you will not see it. Nobody can see it. And this is a key factor, because the fact that nobody can see this device or detect its presence means that you're not negligent in not knowing that it's there, because there's nothing that you can do to prevent or to detect this kind of device inside. And this is a key point from a legal standpoint. So we built this device as a proof of concept because we wanted to say that EMV skimmers are the likely next step after Magstripe skimmers. We move away from the Magstripe. What do we have? We have the chip. So criminal activity will focus on the chip because it is possible to do so. So we predicted that skimming the chip would become extremely appealing, and because the interface is accessible, you have to be able to put your card into the point-of-sale slot. So this means that other things can go inside there. It becomes impossible, as I said, for the user to verify that, and it could go undetected for a very long time. So these were our predictions. And after we made the first presentation about this, of course, it came out that actually there were real chip skimmers installation in the wild that have been reported after our talk, but they were dated before our talk, which is great because we take the credit in exposing the issue, but not the blame for triggering it, because they were dated before. So that was perfect for us. Thank you. And this is much more professional looking than ours, okay? So this is a real unit made by criminals. It has a serial number on it, which should worry you very much. I don't put serial numbers on the PCBs I make, okay? And also, who can tell me what that little wire that goes up and down is? Can you tell what that is? Yes, it is an antenna. So it's even much more professional than ours. In ours, you would require a special card to plug it in and to download the data. Here, you can just sit in the nearby Balzac coffee, whatever you have here, and then just get the data uploaded to you via Bluetooth. So this is scary. And if you can see the plastic piece on the bottom, so that's actually the plastic, the gray piece there. Okay, it's the same model. So what they figure out is that they could unplug the plastic piece and they could put it inside with this skimmer hidden inside. So very professional. So this is a real threat. It can be hooked easily with just a few seconds with the device. It is powered by the point-of-sale device itself. Data can be downloaded wirelessly or with a special card. It takes little development effort. We did it in 2 weeks, and it's cheap. It doesn't cost too much. So this is a real problem. It will happen. It is happening now. Cheap skimmers, they're there. They can be there. So what can you do with a cheap skimmer? The question becomes that we accept that these devices can exist. What can you do with such a skimmer? So smart cards, it's a very simple protocol. You can read, you can send commands to them. You send a request and you get a response through APDU messages. The Emv skimmer can intercept these messages, so it can log them, and it can also man-in-the-middle them. So it can decide to prevent certain messages to reach the card, and it can send fake responses to the terminal, okay? Like a network, TCP, IP, man-in-the-middle, whatever. Now, This is basically a summary of what the EMV is. EMV is divided into these main 4 phases. First of all, we have initiate application processing, where the terminal gets to know the card. Ask the card, hello, what are you? What kind of features do you support? Are you a Visa? Are you a MasterCard? What's the application that I'm going to select? So application might be the Visa application, the MasterCard application, or the debit application. Then you have the card authentication. So we authenticate the card. And this can happen in several different ways, which I'm going to talk about. Then you have the card holder verification. So you verify the person. You authenticated the card, now you verify the person. And this is done with the PIN. The PIN is the card holder verification, or the signature, it depends. And then you have the actual transactions. So there are many problems with the way this protocol has been designed. The first problem is that all of these steps are separate and they are not strongly tied together. And this is one of the main issues. The second problem is that most of the data that is exchanged here is completely unencrypted. So like your credit card number, your name, it's all exchanged and it's unencrypted. And the third problem is that the backend, so the bank, relies on the correct operation of the terminal. So the terminal is not just a dumb middleman. It is something that is essential to maintain the security of the protocol. So this is not an end-to-end protocol by any means. So these are the 3 main issues within EMV. And you will also see that in the way that EMV is being designed, it has a lot of backwards compatibility issues, and some problems were patched with newer version and so on and so on. So it's something that is definitely over-engineered and not secure at all. So the first thing that you can do, which was surprising to us, but it's trivial, it used to be that you can do a Magstripe clone from the chip. Now you can still do that. You can get an exact copy of the Magstripe except for 3 digits. So 3 digits that you need, which are on the Magstripe, are not on the chip. Other than that, you can do it. And this is the CVV. So this means that you cannot clone to Magstripe right away unless you brute force all the 999 CVVs. And we know that in IT nowadays, 999 is such a large number, isn't it? It is staggering, 999, wow. So yeah, so that's the whole security from cloning from chip to Magstripe is right there on these 3 digits. So, and also, there are a lot of websites that surprisingly nowadays, they don't ask for the CVV, like, I don't know, Amazon. So if you buy to Amazon, you don't get asked for a CVV. So I got frauded multiple times with data that was skimmed from my card and that was used without the CVV. So of course you get your money back, okay? So it is a little hassle for you, but it's not a big deal. So you waste time, but you will get your money back. And only goods and services can be acquired by the fraudster in theory, because in practice there are companies which they only exist to convert goods and services into cash. But anyway, you will get your money back. So there's no liability shift here, okay? But it still gives you an idea of how things could have been a little better from the beginning. Now, if they guess the CVV, that's a different matter on its entirely, okay? But, I don't want to dwell into that right now. So that's the first thing that can happen, which shows the fact that lots of data is not encrypted. The next part is offline data authentication. So EMV introduces a way to authenticate the card so that you know that the card is exactly yours. And in principle, this should work. You have a smart card, very powerful. There's no reason why this shouldn't work. Now, there are 3 ways to authenticate a card. There's the basic way, which is called SDA, Static Data Authentication. There's a better way called the Dynamic Data Authentication, and there's an even better way, which is called the Combined Data Authentication, CDA. Each of these methods patches the flaws of the previous one. And these offline data authentication methods were introduced to support offline transactions, so to give you the ability of doing transaction completely offline. So they're never used by ATMs, which they only go online. And nowadays, in theory, you should only see DDA cards, not SDA anymore. So one of the first issues, so what's SDA? SDA means that you have a static signature, which means that if you can read a card, you can copy the data and you can copy the signature. So the signature is basically worthless, so to speak, because there's no challenge response mechanism involved there at all. So if you're offline, you can just present a valid signature that you skimmed somewhere, and then you can just fake the transaction, because the transaction does not go online. Nobody will verify that. The only thing that is verified is the static data authentication, which you're cloning. So well done, EMV, in introducing secure offline authentications. So DDA was invented, where a random number is being exchanged. And we're going to talk about that, so that you have a challenge and response. But there was also a problem with that. So they invented CDA, where they finally do the authentication and the transaction at the same time. So this is to explain how EMV is basically patched. And CDA is, to me, not useful, because you can always fall back to previous authentication methods. You can always fall back to SDA if you want. So offline transactions are insecure if you support the EMV standard as it should be. And now when I mentioned the random number, there's a very extremely nice and brilliant paper for people much more clever than me, which are the fine people at Cambridge, where they highlight the pre-play attack, which this paper really highlights the poor design choices which were made with EMV. So the unpredictable number, which is used to secure the dynamic data authentication, so the dynamic component is the random number which is being exchanged, it is generated by the terminal, not by the backend. So if you have terminals where have a flawed random number generator where you can predict or manipulate random numbers, you can effectively clone a transaction. And you have what they show in the paper, that there are certain terminals where their definition of random number is that you need to give back 10 different numbers. And even if they repeat themselves, well, they're random, because the PCI compliance said that the test mandates that you're going to give me 10 numbers and they all got to be different. So that was the definition of random, which is awesome. So what you can do, you can collect transaction data from a genuine transaction, and when you see that random number popping up again, you replay that transaction. Luckily, there's one limitation here. You got to be in the same country, you got to spend the same amount, and you got to be in the same currency and on the same day. Not on the same merchant, because the merchant information, it does not take place in the transaction between the card or the terminal. It is something that only the terminal knows. But if you fit within these conditions, then you can replay a transaction. You don't even need a valid PIN, and your transaction is cloned 100%. So let's think of this in terms of liability. We're not talking about mass fraud here. I'm not going to say that they can clone millions of cards right away. Let's think about the single fraud that you might receive and the liability that is shifted to you. All of these little attacks, they practically destroy every argument that would shift the liability to you. And this is the key of this talk and why it is important to talk about these things. So if there's a fraud, always check if the same random number was used in the same country by a different terminal, or if the random number of the terminals can predict it or not. If the bank cannot conclusively prove this to you, then there's a chance that this attack might have happened. Of course, even if it might not have happened, just the chance that it could, and the fact that they cannot prove it, means that they cannot shift the liability to you. And this is very important. Now, I'm not a lawyer, okay, so I'm not giving you legal advice, but this is how it is. So, and of course, there's also one other thing, which is called the ATC, the Application Transaction Counter, which gets increased every time you use the card, which can also be used to detect this kind of frauds. And all of this detection, by the way, none of this is done nowadays by backends whatsoever. So what they could do, they don't do. And this is why it is important to know about these things. Second attack, still done by Cambridge, PIN verification wedge attack. So this is the way the PIN is verified by the terminal. The terminal asks the card, is this a valid PIN? And then the card says, yeah, sure, or no, it's not. That's it. There's no authentication, there's no encryption whatsoever in the basic form of this mechanism. The response is not encrypted. It's just a yes or no. So of course, a man-in-the-middle device can just spoof the response and say yes to any PIN and create a so-called yes card. Now, this specific attack was anticipated by a substandard of EMV, which is called the Common Payment Application Specification. But guess who's checking this specific occurrence in backends? Nobody so far. We've done consulting for many financial entities in Europe and abroad. We have never seen detection for these kind of attacks, which takes correlation of 2 bits. If these 2 bits are both 1, you're good. If one of them is 1 and the other one is 0, then it's not good. And you know mathematically that this attack takes place. But this is too difficult to do. So this is one example of this fraud taking place. So we have a clean run where the PIN gets transmitted. You see, it is the little squares. We obfuscated the PIN, 1, 2, 3, 4 there. And you get a response. And in a man-in-the-middle attack, you can just intercept that and then force saying yes. And you will never relay the actual PIN verification to the card. So the card will not know. So where does the detection lie? The card knows what happened, and the terminal knows what happened. Each has their own view. And the card signs this data. So you can correlate the cardholder verification method results generated by the terminal and the so-called issuer application data, which is generated by the card. These 2 pieces of information, they will tell you if the terminal has verified a PIN offline and if the card has verified a PIN offline. And when this attack takes place, the 2 mismatch. And the EID is signed, and the CVMR you cannot intercept with a shim because it happens between the terminal and the backend. So this can be easily detected, but it's not being detected. So this is one thing that you should ask if you're involved into a fraud. You should ask the bank, please show me the EID that was exchanged. Please decode it for me because it's vendor dependent. And also show me the CVMR, and let's see if they match. That's one thing they should provide to you. Now, our contribution to chip and PIN attacks was to take this even further and say, okay, let's assume they fix this flaw. Is the PIN protected? Can we still do something with it? And we discovered the Cvm Downgrade Attack. So the card tells to the terminal how the cardholder should be verified with what is called the CVM list. So sometimes you might use a signature, sometimes you might use a PIN in plain text. You can use an enciphered PIN with DDAs. Who gets to decide that? The card tells to the terminal, this is what I support. And then the terminal can decide. And the card also tells the preference of supported methods. So the card can say, I want to try signature first, but if you're not ready to commit to that, let's use a PIN, offline PIN. And if you don't want that, let's use an online PIN, and so on. And this is the CVM list. So what we discover is that even if this information is signed by the data authentication phase, which is supposed to authenticate the card and the data on the card, if you tamper with it, the terminal will still be so happy to parse it and accept it and honor it, which is a problem on its own because, and I'm going to get into detail for this. So this is the CVM list. These are all the fields that you can have. So we're interested to plain text PIN. So you can have enciphered PIN, which means that the PIN will send encrypted to the card. The response will still be unencrypted, by the way. The response will still be yes or no, but at least the PIN is encrypted. And you have online PIN, which means that the card will never see the PIN request because it's between the terminal and the backend. Or you have signature, or you also have no PIN required, or no CVM required whatsoever, which is what we use in toll roads in Italy. We pay with a credit card, there's no signature, there's no PIN, because we fall back to that. So we asked ourselves, if we use only DDA cards, which is what banks say it's the state of the art, and we invalidate the signature. So this is the problem. There's one piece of data on the card, which is called the issuer action codes, which specify which failure conditions should trigger an online transaction. So this is what happens. I'm the card, and I'll tell you to the terminal, please do not deny a transaction without attempting to go online, even if my signature fails. So let's think of this in terms of security. You have data which is signed, and you can tell to the terminal what to do if the signature fails. That seems obvious to me, right? It's like, hey, I want to go out with you. I really don't. Yes, you do. Okay. That's how it goes, right? So in every test terminal and backend, we were able to manipulate when it was necessary these action codes so that if we tamper with the CVM list, we would not be rejected offline. And guess what? The CVM list is parsed by the terminal and it's applied. So we can tell the terminal what to do, which means that whatever card you have, we can tell the terminal, please verify the PIN offline, which means that a skimmer can always force the terminal to transmit what is input on the PIN pad as a PIN to the card, which leaves for interception, which makes the whole liability fall apart. And this is one example here. We modify the CVM list. So this is a normal card which goes online, because you see on the left side, the PIN verification phase is empty because there's been none, because that went online. But on the right side, there's our man in the middle, where we actually invalidate the CVM list and we force the PIN transmission to the card. And keep in mind, the backend will know that the signature failed. They just don't care about it. So from a protocol standpoint, you could say that this is somehow anticipated, the signature fails. But since the data authentication of the card is a separate step from the authentication of the cardholder, since those are treated separately, then the two phases, they don't use the knowledge gained from the other. So that's why you can always force the PIN to be transmitted plain text. The way you detect it, well, you have offline data authentication failure, and you might even correlate how the card was issued. You might have a card which only has online PIN in the CVM list, so you can tell if the offline PIN is requested, something wrong is there. But that's simply too much data to keep on the backend. The backend would have to know every configuration for every single card, which to me is not unreasonable, but apparently it is. But you could at least reject every transaction which doesn't pass offline data authentication. But sometimes you also don't get offline data authentication processing at all. So, and one more important thing, even if you would have these markers, these are not conclusive evidence, either positive or negative, because as a skimmer, I can always reset the terminal as soon as I get the PIN, which means that the backend won't see anything at all and won't get any data from the transaction. So this is a design flaw that cannot be even detected if you implement it completely covertly. The only way to fix this is to have the firmware on the point-of-sale device to refuse offline plaintext PIN verification all the time if you know that your cards don't support that, or in case of signature invalidation at least. And this is a big problem with liability, because you cannot say that the EMV protects your PIN. Despite the card configuration, you might have a DDA card which doesn't even have a PIN on the card itself, and I would still be able to do this and to see your PIN. So if I steal your card afterwards, of course I will need your physical card. These are the scenarios that we're talking about. Then you will never be liable. But the classic case is that if you lose your card and it gets used and it has chip and PIN, they will tell you that you're liable if it's used with a PIN, because they tell you that you're being negligent, because maybe you had your PIN written down in the bag or somewhere, but it doesn't matter if it's the truth or not. They will use the technology of EMV, which is flawed, against you. And we see this all the time. And we consult cardholders into preventing these kind of claims by asking for the right data. And which is why I'm giving this talk right now, to let you know what you can ask in order to prevent these kind of things. Because even if we're not talking about millions of people being fraud, I don't care. As long as one person loses, I don't care, 100, 2,000 euro, because this technology is turned against them, I don't think that's right. And I think as an IT security community, we should work against that. Thank you. So going back to the PIN verification wedge attack, the one where we say yes or no to the PIN that was discovered by Cambridge. In their first paper, they say that depending on the CVM list, whatever is specified, cheapest signature or online PIN, they tell that their attack is not applicable to certain cards. And at the time when we released the Cvm Downgrade Attack, we thought of combining the two, but we didn't actually try it. This summer, we tried it. There's no reason why it shouldn't work. And guess what? It works just fine. We can combine the CVM Downgrade Attack and the PIN verification wedge attack to use stolen cards regardless of their configuration. We can use cards which are only meant to go online. We can use cards that only have a signature. We can use cards where the actual chip on the card doesn't have the PIN stored. There's a command which you send to the smart card saying verify PIN. Certain cards do not support that because they're secure, and they don't even have knowledge of the PIN. But if we combine the two attacks, we downgrade or upgrade the card depending on its configuration, and then we force a fake offline PIN reply. And of course, this works. Regardless of the card configuration, we were able to test it with every card, with different stores. We tested with our own cards. We were able to fraud our own cards with PIN, which is 1234, which is not our actual PIN. So it doesn't really matter. The backend is not even smart enough to understand that offline PIN verification took place on a card that has no PIN whatsoever, even with cards with a signature. So the Cambridge PIN verification wedge attack can be applied to every single card. So if the bank will tell you, oh, but we only have DDA cards, and you don't even have a PIN on the card, or you only go online, it doesn't matter at all, because you can always downgrade. So this is an example of that run. Again, on the left side, there was no PIN verification whatsoever, and this card was set to do PIN online. So we do two things. We do the combination of the two attacks. First of all, we do change the CVM list so that the PIN is being asked to the card, and then we reply, yes, this is my PIN. Of course, 1234 is my PIN. And you get both detection markers here, because the signature fails, and the card tells that it has verified no PIN, while the terminal will say, I have verified a PIN. So we have two things that we can spot. No backend that we have tested so far was smart enough to do this kind of correlation. Not on the same day, not after a week, not after a month, nothing. So this is a main problem here. There's another problem. EMV supports the concept of transaction certificate, which is the final thing that happens. The card will spit out to the terminal a transaction certificate, which will be the proof of the transaction. This transaction certificate is not immediately sent to the backend. Sometimes it's not sent to the backend at all. And it should only be parsed when a dispute arises. So guess what? You can change that. You can put it to dead beef, whatever hex, lead sentence you want to put, and the transaction will go through right away. So what is supposed to be the actual proof of the transaction never gets checked. So I could potentially fake my transaction certificate on all of my transactions and then claim all of them back and ask them, look, at the transaction certificate, it doesn't really make sense. And the bank would be, obliged to tell that I'm right. Of course, that would be not very smart, but this is to give you a proof of how flawed this protocol is. And this also means one thing, that when you see on the card the transaction certificate, the issuer application data which is what allows you to detect the PIN verification wedge attack or the application transaction counter. Since those are printed on the receipt from this last phase, they can all be faked. You can put whatever you want there. So if the bank will ask you to see the receipt, or if they will show you the receipt as a proof of some metadata that is important, you can always say that you don't trust that, because you can tamper with all of that. So whatever is on the receipt with these specific parameters can be faked. No problem about that. And this is also important to know. So the banks will have the following arguments in case of EMV fraud. PIN verification cannot be compromised with EMV. And ciphered PIN guarantees security. Online PIN cannot be intercepted. And plaintext PIN is kept for backwards compatibility only and can only be forced if you tamper the terminal or on specific configuration. All of these are not true, as we've shown. We can always fall back to plaintext PIN. So all the mechanisms that are there to protect the PIN verification, they do not work. And we don't tamper the terminal itself. I could even have my own card which has NFC Bluetooth connection to a real car, and it will just do this kind of transaction. The terminal is intact. We don't change the firmware on the terminal. We don't do anything wrong with it. Okay, so don't take the fact that we insert as shim as an example as terminal tampering, because that's not the case. It could be very well be my own card. So liability falls apart, especially in the Cvm Downgrade one, where you can have no logs in the backend. So if you have a dispute, the bank should at least provide you the unpredictable numbers from that same terminal or from other terminals that were used with your card on the same day. They should provide you the terminal verification results. They should provide you the issuer application data. They should provide you the application transaction counter. All of the metadata that I've shown to you, they should provide them to you in order to give an analysis of exactly what happened. If they don't, they have no claims. And even if they provide them, it really depends on what's going on. So depending on the different kind of attacks, these are the things that you should ask. And it is essential to acquire the backend data, not only the one that has the terminal, and especially not the one that the receipt has. And so the unpredictable number will give you the freshness of the terminal random numbers. The ATC will give you if there are any gaps in the transaction, which can make you understand if something fishy went on. The terminal verification results will tell you if the offline data authentication failed or not. And the cardholder verification method result will tell you exactly, what happened, and they must agree with the issuer application data, which is signed. If they don't agree, then an attack went on in spoofing the incorrect PIN. So these are the things that you should ask. So what happens when we ask for this data? Two options. When we start asking for this data, the bank sees that the claim goes forward, because some people, they just want to settle before, or they get scared and they lose their money. And this is what actually happens. I have experience with this. So if you get to ask the data, at some point, it depends on the country. Again, I'm not a legal expert, but this is how it is. You go to the arbiter. And the arbiter, guess what? It will tell you that the burden of proof in fraud claims shall fall in the owner of the payment infrastructure. And at least in Italy, they rule that the PIN can be acquired in many ways that are outside the cardholder control. Now, this is the interesting thing. Every single fraud case where the liability, they attempted to shift the liability to the customer, the bank tried to do this anyway, even if there were dozens of legal precedents with response number one. So now we're in a state where this kind of response is just, as it goes in law, is just quoted from previous cases. They won't even bother in doing the whole dissertation. They say, go track, like they do in Law and Order in the US. Go and track in 1984, there was Johnson versus Smith. This is what happened. So that's what it is. So, but they try anyway, even if they know, because what do they have to lose, right? So it is important to know that at the end of the day, in most countries, you are protected and they can never use the technology against you. But you need to have to show that you know the technology a little to know what to ask for. Because number two, in some cases, as soon as we ask for detailed logs, guess what? The bank settled and we had a refund. I don't know why. I don't know if it's because the data would have proved that some fraud was taking place. I have no idea. The only thing that I know is that the classic vendor response in these cases is there are sufficient security mechanisms in the payment industry to prevent these kind of things to happen. This is a classic response that Visa, MasterCard, or any bank will give you because, and in a way you would understand them, they will never tell you that, of course, EMV is flawed. They would just tell you that there's a sufficient number of mechanisms in place. But as soon as we see fraud cases being, shifted to the customer, as soon as I'm able to fraud my own card and nobody calls me, I think that there's something wrong with the system, especially where the technology can very well do end-to-end encryption from the card to the backend, and the terminal would just be a dumb relay. But this is not the case. And as long as we don't admit that there are these flaws, we will never fix them. And there's one more thing that I would like to say. In the US, very recently, they're started moving after saying for many years, no, we're never going to move away from the Magstripe. They're going to move to the chip. And since, for whatever technical reasons, they're going to do chip and signature. They're not going to do chip and PIN. So they're going to remove all of the PIN verification part, which in some way, it's a good thing. Because if you have a chip and signature, you're not liable. The chip protects the actual transaction, which is fairly well protected if we ignore the unpredictable number thingy. But the transaction, that's the only thing that is a security issue there, but that can be fixed. If you would remove the whole cardholder verification phase, then the cardholder is not liable. So incidentally, by doing less, they're actually doing more from a security standpoint. So, things can be done. And also in the Netherlands, after one of our presentations, they patched every single point of sale device in order to refuse plain text PIN verification. Of course, they did that only for local cards. And I don't think that the detection of local card uses a data which is actually signed. So I think there was a bit of a problem there. But anyway, so this is how it is. So I think we have about 10 minutes for questions. And before that, I also have a little demo here. So I will show you what happens when both attacks are combined. So this is how we do them. We have an FPGA, which acts as a shim between a real card terminal and an actual point-of-sale device. So you see them here. That's a terminal. That's a reader attached to the laptop, which is doing man-in-the-middle through the FPGA. And the FPGA will have a smart card which goes inside the terminal. So all of these attacks, we test them with the code running on the laptop. In this case, we're using one of our own cards. We plug it in. So this card has no concept of offline PIN in its CVM list. So we do two things. We downgrade the CVM on the fly. So we type the amount. And then a PIN is being asked. So the fact that the PIN is being asked right there before going offline means that the first part of the attack was effective, because we convinced the terminal to be so kind to ask the PIN to the card. And the second attack you will see is because we will just type 1, 2, 3, 4, 5. And that gets accepted. And then the terminal goes online because we said yes. And from the logs, we see that we can tamper both of them, and so on. So that was the demonstration. Thank you. And before answering questions from you, I got an email from a journalist today. Maybe he's here, I don't know. He asked me 3 things. The German finance industry says that the weaknesses of EMV in general would not be an issue, as point 1, SDA cards would not be given out to customers. Irrelevant. SDA is always present as a backward compatibility into every card. And this is the reason why you can use your card and go abroad, because some terminals don't even know what DDA is. So every EMV card, by the standard, has SDA and DDA, if he has DDA. If he has SDA, the only SDA. But every DDA card also supports SDA as a capability. Second point, fallback transactions would not be allowed. This might be, but it's very hard to accept that. Very hard. Because if I come here as a tourist, I can use my SDA card. And even if they would do something smart, like detecting your own card, I can always fake a foreign card in order to do PIN interception. I could make up Mickey Mouse credit card, totally fake, in order to intercept the PIN, and you will never know, because I can always reset everything before going online. So I can always get the PIN that you're typing on the terminal. Third, there were no German EMV cards that were breached ever. I cannot possibly comment on that without breaching a lot of NDAs. So, any questions from the audience? There.
Please use the microphones.
Have you ever played around with the idea of faking the entire card? I mean,
yes.
If you skim the number and then you just use the smart card to play.
Yes. So we skim the real card, so the skimmer can read the card independently. We fake a card, or we use another card, a previous card, like an SDA card. We get to the point where we do PIN verification, we intercept the PIN, we reset everything, and then you would just see that the terminal resets, or it will send you reject transaction and it will try it one more time.
The reason I'm asking is because it's relatively easy to steal the number itself, whether visually or for magnetic stripes.
Yes.
And then if you can create a fake chip card that presents itself as that number, but you actually control the chip, then you can accept whatever PIN and...
Yes, but this is only for PIN interception, where you actually go to the actual transaction that you cannot fake, unless it's offline. So all of this is for either using a stolen card without knowing the PIN, or to intercept the PIN on any card, okay? Transactions cannot be faked unless you can predict the unpredictable number. That's the only condition, okay? So this is important. Thank you. There. Hi.
So were we talking only about those card readers that you find in shops? Because like in ATMs, like as far as I know, if you go to an ATM and enter your PIN,
right,
the PIN is encrypted in the touchpad.
Right.
And this is sent to your bank. And this is like not that bad. This is actually quite okay,
yes.
Right?
So there are two things that I have to say on this. First of all, we never play with ATMs because it's extremely difficult, even as professional, to get to audit them. But and ATMs is, as you say, they should all go online. I can tell you from personal experience that at least in Italy, not all of them go online. And it's very easy to understand that. If you type the wrong PIN, sometimes it gets rejected right away. Like it takes even a millisecond. And you can also check by reading back the logs on your card what was actually used as a PIN verification mechanism. And at least in certain ATMs, I think this was in the migration phase, they were not checking the PIN online. But I cannot say what is it today. What I would say is that I worry much more about point-of-sale devices when it comes to PIN interception, because there are so many of them and they're so much more insecure. You know, I can gain access to a point-of-sale device much more easily than doing it on ATM. I don't have cameras pointing at me. I'm not outside a bank. You know, I can collude with the merchant. There are so many ways. And from the liability framework perspective, all I care is about one point of sale in one city where this might have happened, right?
Yeah, I agree 100%. I was just thinking like what to tell can I tell my grandmother that, okay, if you use an ATM, you are secure because your PIN gets encrypted on the touchpad, no matter where you are, in Italy, US, Russia, whatever.
In principle, yes. But in our line of profession, I cannot tell you 100% for sure. I don't know because we never tested them. But in theory, that's what should have happened, yes. You have much better chances of being safe from EMV protocol interception on ATMs, but you're much less safer from actually physical interception because the ATM skimmers that I shown, they're still there. So, you know, at the end of the day, you can always say that there's a hidden camera and the whole liability falls apart. These are just, you know, more cases to say that the PIN is not really a good way to make you liable.
Thanks.
Thank you.
I've got a question regarding online payments,
Yes.
not regarding EVM. In some countries, I know of Holland, they ask for some date of birth and then a password. You know anything about the security behind this and liabilities?
So a friend of mine called Adam Laurie from Aperture Labs, very smart guy, does all the RFID stuff. You should check his work. Once had a card with, you know, secure code by Visa and MasterCard, where you go online and in order to provision it, you know, you have a password, and then if the password doesn't work, it will ask you a question like the, you know, name of birth, the birth date, and so on. So his daughter wanted to buy something with his credit card. And Adam gave the credit card to the daughter and says, let's see if you can hack it. After 10 minutes, she came back and she totally reset, of course, the whole secure code thing with data that she wasn't supposed to know because there was a secret question or a secret answer along with the birthday and so on. So, you know, security and birth date and other kind of data, they don't really match together, you know? We're struggling here to get proper SSL encryption from browser to websites, you know? I know, you know, it's just, you know, they're meaningless at the end. They're not, they might have been something that I would have vaguely respected 10 years ago, you know, 20 years ago, but nowadays, you know, no, just no.
One offside question, please.
I have a bunch of questions from the internet. First one, are the cost of proper security actually larger than the current cost of the insecurity?
So this is the classic argument from the bank. They say, okay, I have like 0.001% fraud, so why would I care? If the customer, if the cardholder gets the money back, yes, I mean, you can argue that the time spent in getting your money back is of course as a cost, but in principle you could say, yes, of course, but this is the issue here, you know? They don't get their money back if they don't fight the claim properly. So when you see the statistics about fraud, they don't put into account these cases where liability is shifted to the customer. And that's my whole point there. Even if you have one person which loses 2,000 euros that they didn't lose because they were negligent, whatever that means, you know, they shouldn't lose this kind of money. So I don't care if that's 0.0000001% of the total profit, it shouldn't happen. So we handle about a dozen cases, and that's, you know, that's more than enough. And we know that if we, which are a very small company, we handle a dozen cases, maybe there's so many more. And maybe there's so many more people that they didn't get their money back. So yeah, that's, you know, that argument is not relevant to the kind of discussion that I want to have here.
Okay, 3 last questions. Andrea will be there for more questions for you, so please.
Yes, approach me anytime.
Okay.
3 more questions.
Number 4, starting. 4, 2, 1.
On the just one quick comment: the CVV on the Magstripe isn't the same as the CVV on the back of the card. Those are 2 different values. That was
correct. Those are 2 different ones. Yes.
At the beginning, but in a similar vein to what's to the price or the cost of the attack to what's coming out. You said you don't necessarily have to have a wedge and a stolen card if you're doing downgrade attacks, for example, because you could maybe have a card that communicates to the stolen card via Bluetooth and
yes,
have that as the man in the middle. But that would make an attack at a POS pretty expensive for the attacker. So it seems that that's a somewhat unlikely attack scenario. If I stole cards, I think there's more.
Is this a question?
More. Yeah, is that, I mean, well, that whole cost of attack thing applies to the attacker as well.
So there are 2 aspects here. So the first aspect is that from a liability standpoint, we don't care about how likely it is. As long as it can happen, then from a legal standpoint, then, you know, you are not negligent if this can happen. The second thing is, if I would be a criminal, this is what I would do. I would skim every single point of sales that I can in a way which is covert. And then as soon as one card gets stolen, There's a very nice database where, oh, you stole that car? Hey, I have the PIN for that. So this is something that you can do. Now, how likely is that happening now? I don't know. I don't think it's very likely. How likely is that maybe 5, 10 years from now when the Magstripe goes away? Much more likely. So we need to address this now. And having an industry which is pushing this technology as the holy grail of security doesn't help. So this is my whole argument here. So you can see both sides.
Number 2, please.
Can you comment on NFC payments?
Yes. So NFC payments, it's a complicated matter. There are many ways of doing them. Some of them, they expose very similar vulnerabilities to what you see here, because it's actually EMV going wireless. So sometimes they have this classic downgrade mechanism. You can harvest the CVV, they have a dynamic CVV you can harvest and then replay. So they have their own set of issues. It would require another 1-hour talk to address them, but let us say that there are similar issues there as well, and it's not something that was well thought of from the beginning, okay? You have a smart card, the actual signing of the transaction, that is, except for the random number, it is done correctly. If they would just stick to just that phase and the random number comes from the backend, that would have been so much simpler, minimal design, end-to-end, easy. I want to pay this, done. And the fact that they're not following this also reflects on NFC in a way.
Another offside question, the last one.
Thank you. What precautions does your team take to prevent being legally stomped on by the bank as you probe their weaknesses?
So first of all, in many of our consulting, we were actually paid by the banks to do this. So in our experience, most banks, they don't consider these to be serious issues, but not all of them. There are a few of them which are very exemplary in the way they consulted us into exposing the casual techniques, and they have security teams which they care. They are aware of all of these issues, and they know that it's a political fight. So I don't want to blame the entire industry. Second of all, from a legal standpoint, I mean, we have the Cambridge group, which preceded us. We have done our research. All of this you can read through the standard. I mean, you know, in our job, it's a double-edged sword all the time. Everything that we do, 99% of the talks here, you do something which you think is for the greater good, but it can also be used maliciously. This is the thing. We're not, if I think of something, I think of an attack. There's no reason why you don't have 20 other people thinking of that before me for criminal activities. So, you know, there's no reason to keep this quiet, you know. That's what our industry does. And I think most of the audience here agrees to that. And it's a well-known, accepted fact of the industry. So far, we didn't have any problems at all.
Okay, sorry, that's it. We have to finish now. Yeah.
Thank you very much. I hope you enjoyed it.
Andrea.
And if you want tomorrow, come see this.